This is Jack Jackson. Today we're going to be talking about applications of exponential functions. So we're going to be applying what we've learned about exponential functions to some real-world situations. Now it turns out that exponential functions are probably the second most important type of functions in terms of applications. Probably linear functions are the most important. We've studied those a lot earlier because they're so useful and they're pretty simple. Probably the next important in terms of how often they're used are exponential functions. Now we've already seen that linear functions are those functions that have a constant rate of change, that is a constant slope. And we're going to find out here in just a minute that exponential functions are those functions that have a constant relative rate of change, that is a constant percentage change. And this rate we're going to see is the base minus 1. And so these two ways of growing or decaying, increase or decrease, growth or decay, are two basic ways that functions could experience growth or decline. And these have lots of real-world examples that model them. So let's look at a couple of different examples here and things that we can do. The first thing we're going to look at here is what can we do in terms of taking a exponential function. If we're given 2 points, can we find out the formula? And we know that we can do this. The base is found as y2 divided by y1 to the 1 over delta x power. Okay, and this is going to be constant for an exponential function between any 2 points on the graph or in the table. So if we start with a pair of points, okay, so 2 points where they have different x values, we can compute the value of b with this formula here, and then we're going to obtain a unique exponential function that goes through these 2 points. Just like we could find a unique line going through the 2 points, we can find a unique exponential function. And then one way we could do the formula is to use the point base formula. Just like we could use the point slope formula in lines, we can use the point base formula here, y equals y1 times b to the power x minus x1. You could also use the base Y-intercept formula, y equals y sub 0 b to the x, if you plug in a point for x and y and then solve for the y sub 0. That's an alternative way. If we want to use this form directly, we just directly put in the value of x1 and y1 where that's one of the points. Okay, let's see if you can do this now on an example. So throughout these notes here, you're going to be asked to do some work, and what I'd like you to do is to stop the video, press pause, and then go on and figure this out, and then come back when you have an answer. Even if it's not right, at least attempting this will help you out a lot. So here's your first exercise. The population of a region has been growing exponentially at least since the beginning of 1980, when the population was 34,000. The population at the beginning of 2010 was 40,000. Write a formula for the population P as a function of the year T. Graph the function in an appropriate window using your graphing calculator. Make a table of population values in 5-year increments starting in 1980, and again you can use your calculator for that. Use your formula to find the population in 2012, and assuming that the population continues to be modeled well by this function, when will it first reach 50,000? So see if you can work this out. Come back when you've gotten your answer. Press pause now. So I have the solution worked out here. Okay, since it's been growing exponentially, we know that this base, b, should be constant. How do we find b? Well, it's y2 divided by y1 to the power 1 over delta x. So y2 for the second point was 40,000, y1 was 34,000. By the way, 40,000 over 35,000, we can divide top and bottom by 1,000. We get 40 over 35. Divide top and bottom by 5, and we get 8 over 7. So that reduces to 8 over 7. Delta x is 2010 minus 1980, which is 30 years. So the power is 1 over 30. So we can take 8/7 to the power 1 over 30, which you can see down here in the calculator. And I went ahead and stored it as b, so I don't have to type these numbers in again. So this avoids me having to type in again 8/7 to the power 1 over 30th or typing in all these digits. Later on, I'm just going to use B because it's stored as the right thing. So there's our base B, approximately at least. As long as we keep all the digits in our calculator, we're going to be fine. We don't want to, for example, just round this off to 1 or 1.004 when we're doing further calculations. Now, what's the point base formula? Well, we use that same formula. Y equals y1 times b to the power x minus x1. Y1 was 35,000, where b is what we just figured out, 1.004460967. And the power is, well, we're going to use t instead of x. We're going to use p instead of y, or p of t instead of y. And so this becomes the power of t minus 1980, because in 1980 there were 35,000 for the population. Check that out. If you plug in t equals 1980 here, you get a power of 0. So 1 to the 0 power, 1 point whatever to the 0 power is 1, times 35,000 is 35,000. So it does go through the point 1980, comma 35,000. And you could check it with the other point as well, which we're actually going to do here in a minute when we check our table. So graph it. So since I already have this stored as b, I just typed in 35,000 times b to the power x minus 1980. Be sure I put parentheses around the x minus 1980. And we're going to graph it from 1980 to 2020. And I marked off the x-axis in 5-year increments. And we know it's going to go from 35,000 up because it's increasing. So we could have actually just started at 35,000. I started a little bit below that at 30,000 and went up to 50,000 and marked the y's off in 5,000s. And you might have to do a little trial and error here to figure out what would be an appropriate thing here to do, okay, in terms of the which window to use. Now make a population table. So we go to table setup. That's on our calculator, table setup, which is second and then window to set up our table. Okay. And we can do this as an automatic table if we start at 1980 and let the delta table, that is the delta x, be 5. And then we see we go x equals 1985, then 1990, 1995, and so forth. So those are your time values in years. That's the actual year number. And we can, by the way, let's check it because it should go through 1980, 35,000, and it should also go through 2010, 40,000. Let's see, did that happen to show up in the particular table? Yeah, 2010, 40,000 there. Now notice if you put your cursor over there, sometimes you can get a few more decimal places. In this case, we're talking about probably about people here, or some kind of organism that we're measuring the population of. So you're not going to have a fraction there. So these should be rounded off to the whole number person, which in fact they are in the table. So what's the population in 2012? A couple easy ways we can do it. We could actually put 2012 in our table for x. We could actually do, since this is y1, we could do y1 of 2012, which would give us this p of 2012. We can take our formula and plug in 2012 for it. Or you can do it the way I did it here, which is just hit trace on the graph and type in x is 2012 and enter, and it'll tell you the y there, which rounded off the nearest person, is 40,358. And if we assume that this model is still going to hold, when does it first reach 50,000? Now let's back up a minute. In part D, notice that once we had this, basically we were given an x and we needed to find a y. So you could use trace for that, for example, or just use the table. This one goes backwards where we want to, we know the y and we want to find x. So the way to do this on the calculator method is to let y2 be the y value you're trying to reach, 50,000. When you hit graph, that's going to graph a horizontal line. I think I had to adjust the window a little bit here, trial and error, till I found the intersection point. And then I get the population reaches 50,000 when the year is 2060 point something. So notice the 2000. So I went back to the home screen and just typed x and enter, and it gave me the 2060.13283. Took away the 2060, and I look at the fraction of the year, and take that fraction times 365 days a year. That says we're 48 days into the year. Well, there are 31 days in January, so that means we're 17th day, well, point something, so we're really on the 18th day of the second month, so that's February 18th in 2060, if this formula were actually that accurate, that precise. In reality, this may be only an approximation, so we may not be able to pin it down that closely, but early 2060, probably a pretty good bet. And of course, that assumes that this formula is still going to hold. Now, the next thing we want to do is, how do we determine if a relation given by a table is exactly exponential? And if so, how do we determine its formula? Now, again, what we can do is find this b, y2 divided by y1 to the power of 1 over delta x. And we can do that between any 2 points in the table. In fact, we want to do it between all successive adjacent points. And then once we do that, then we'll have this b value. If this b value is the same, then it's an exponential function. Okay, and then we can take any one of our points and plug in this form here in the point base formula. Or we could use the y equals y sub 0 times b to the x formula and plug in a point for x and y and solve for y sub 0, and that will get it to you as well. Okay, let's look at an example here. Oops. Let's see the solution yet. Oops. Put this where I want it to be. Here we are. Okay, so here we have a table of we're going to call the input y. Now normally we use y for the output, but this time I chose y for the input because it's the year, and I didn't use t for the year because I want to use t for tuition. So we have tuition. This is the annual full-time tuition and fees at a university is given by the following table. In the year 2000 it was 1,121. In 2005 is $1,500.15, and so forth, and you can read the rest of those there. So we have just some kind of random years spaced out there between 2000 and 2011. So is this exponential? And if it is, find the formula for it. And then if you have that formula, then use the formula to determine when the annual tuition and fees will first reach or exceed 2,500. And according to this formula, when is the annual tuition and fees, what were they or will they be in 2013 according to their model? Okay, see if you can work this one out yourself. Come back when you're done and we'll check your answer. Press pause now. Okay, let's take a look here. Well, the way to do this is to find b between successive points. And so here you can see the computations. I've got it written out as formulas on the left, and on the right you can see what I actually typed in my calculator to check it out. I did do the subtraction in my head. Those were easy enough. So, but if you're going to do the subtraction on your calculator as well, be sure you put the denominator of the little fraction in parentheses as well. Okay, I think I got my things here backwards. Okay, that looks a little bit better. Okay, so this first one, we have to find b, we go to the table, and let's look up, see if we can see the table so you see where we're getting these numbers. Okay, so we're doing delta x is across here, 2005 minus 2000. So that's 5 years. So I'm going to raise to the 1/5 power, which you can see I did here in the calculator. And we're going to divide the y's. Final y divided by initial y. Final x minus initial x. I guess I should use the right letters here. The t2 divided by t1. And in this case, delta x is really delta y because I use y for x instead here. Over on the formula, I use the generic y for output, x for input. So the change in the input is 5 years, so I'll take the 1/5 power. And then the ratio of the y values, or outputs, t values here actually, is $1,500.15 divided by $1,121. And so you can see how I did that over here in the calculator, and I got approximately 1.06. It's really 1.06 0, 0, 0, 0. At least that many decimal places, it's 1.06. The next one, I do these 2 points here. So the first one I did these 2 points. And the second one I do the second and third point for that pair. Okay, so this time delta x is 2008 minus 2005 is 3 years, so I'm going to be raising to the 1/3 power. And for the y's, I'm going to divide the y's, second y divided by first y, and you can see that there, that I'm dividing the $1,786.70 by $1,500.15. And again, if you look, I got 1.06 at least to 1, 2, 3, 4, 5, like 5 or 6 decimal places. Okay, in a similar manner, I could do the last 2. So I'm doing, those 2 points, then I do these 2 points, and then I do these 2 points. So there's actually 1, 2, 3, 4 of these b's that I need to compute. There are actually other combinations for the first and third and so forth. But if you get all these pairs to turn out, then any other combination you're going to get is going to work as well. And they all were 1.06, at least to several decimal places. And so we're going to use 1.06 as the base. Determine a formula. I could take any one of these points I want, like say the first one, 2000, and then 1121, 1121. And so we got 1,121 here, 1.06 to the y minus 2,000, and that's t. And of course that's going to be in dollars, and that's annual fees and tuition for this particular institution. Now, when you want to see when it first reaches or exceeds the 2,500, that's the t value or the output value here. So in my calculator, I'm going to rewrite this instead of y, where I have a y, I'm going to put x in the calculator. And on where y2, I'm going to put the t value that I need, 2,500, and I picked something here. I think this is 2,000 here that's blocked out here, 2000. So 2000 to 2020, and graphed it along with this horizontal line here. So we're graphing the exponential and the horizontal line, and they cross right there, which I can do a calc intersection, and we see that that's 2014. If we check this with the table, I did a table started at 2013 going up by ones, and in fact you do see that's the first time that it actually does go over. By the way, this one really is a geometric sequence rather than a exponential function, because the domain is just actually some natural numbers. Okay, this doesn't even make sense going back. I'm sure this. First of all, the university probably didn't exist, several hundred years ago. Besides that, this formula only really applies for certain years. Okay, so but it does go up in chunks. You don't have a continuous function here really. Even though we're graphing it as a continuous function, it's really dots along this curve where we have jumps. So the table in a way is really more accurate way of seeing it. But anyway, we see in 2014 the annual tuition and fees will first exceed 2,500. And then when will the tuition and fees be in 2013? Again, I can look at the table or a trace, or from the home screen I can do Y1 of 2013. Either way, I get $2,391.01. Now, I mentioned this at the beginning of the lecture, but it turns out that exponential functions have a constant relative or percentage growth rate. So we've seen that the base b, determined by y2 divided by y1 to the 1 over delta x power, is constant for exponential functions. This base is the common ratio between successive y values when the x values increase by 1. In other words, if the x values are going up by 1 in the table, it is this b value that we're multiplying the y's by each time to get the next y. So we're going to find something else that's constant for these functions. So now often we're interested in the amount of change in a function, but that's just simply the change in f, delta f, or f2 minus f1, or y2 minus y1. However, the amount of change is sometimes not as important as how that amount compares to the original function value. For example, if you make an error, and your error is 5 inches, Is that bad, or is that not that much? Well, it depends on how far we're measuring. If we're measuring, say, from Fort Smith to Chicago, and we're off by 5 inches, it's practically nothing. Okay, but if we're measuring, say, how far it is across my laptop computer, and I'm off by 5 inches, that's a lot. So we're interested in how much that is. Still 5 inches, so the amount of difference, there, or amount of error, is the same, but sometimes we want to find the relative error, or the relative change is a percentage change. So the relative change is, we're going to use the letter R, and at least when delta x is 1, R is going to be the change in f divided by the original f. Okay, so you divide the actual change by the original f value, and so it's often given in percentage form, and it's how much f change is a percentage of the original f value at the beginning of that period. So percentage rates are actually relative rates. So let's look at an example now. Suppose we got a function here, t and q of t. I'll use q for quantity, t for time. And let's say this one could be, for example, quantity could be the amount of money in a certificate of deposit, a CD. And at time 0, we deposit 5,000. At 1 year later, we find out that the value of the CD is $5,250. 2 years after we deposited it, it's worth $5,512.50, and 3 years after deposit, it's worth $5,788.13. So, can we describe what's going on here? What kind of function do we have? Well, we can do several different things. Notice that this is just a sequence because we're actually adding 1 to the year each time. Although it could really be an exponential function because with say positives, or 0 to something, or at least 0 up to whenever we withdraw it for the domain. Okay, so this could be a continuous function. At time 0, we have $5,000. At time 1 year later, we have $5,250. Notice that's an actual increase of $250. That's delta Q. The next time it goes up more than $250, it goes up $262.50. We found that by doing $5,512.50 minus $5,250. We found the 250 by subtracting the 2 before. And finally, we find that $275.63 is what we get from going from year 2 to year 3. But if you look, you divide these. Delta t is just 1, so the base is just q2 divided by q1 to the 1 over delta t power, so it's just q2 divided by q1. Try this out on your calculator. Divide 5,250 by 5,000, and you're going to get at least approximately 1.05. And if we do the next one, we divide out here, divide those two. Notice we're dividing by not the original amount at time 0, but the original amount in the sense at the beginning of the year. So we're dividing $5,512.50 by $5,250, and again you get 1.05. And same for the last. Now some of these may be rounded off just slightly, but it's 1.05 to several digits. So that means the base is constant. We're multiplying each year by 1.05. Now let's figure out what the relative rate is. So the relative rate is we take the amount of change, 250, we divide it by the initial amount at the beginning of that year. So we're taking 250 divided by 5,000, and that turns out to be 0.05 or 5%. The next time we take the $262.50 and divide it not by 5,000, but rather by what it was at the beginning of that year, 5,250. And again, that turns out to be 5%. And the last one, we divide $275.63 by $5,512.50 because that was the beginning of that year's amount. And again, you get 5%. So notice that the relative rate of change is constant. Okay? A relative rate of change is a constant there. So notice that the percentage rate is a constant at 5% per year. So what are we doing? We're earning 5% a year on this particular investment. Okay. So as the time I'm doing this video, 5% a year would be an amazingly good rate to get on a CD. Not likely to be happening right now, but I just made that 5% to make it easier for us to see. So if time is measured in years, like we worked it out, the Q values are increasing at a relative rate of 5% per year. So it's 5% of the previous value at the beginning of that year. That's going to be the amount of increase. Now notice these values here. Notice we have 1.05 for the base. We have 0.05 for the rate. That's not a coincidence. The base is always 1 plus the rate, and I'll show you why that's true. It's not an accident. Look, what is the rate? The rate is delta Q over the first quantity, or delta Y over the first Y. So that's Q2 minus Q1 over Q1. Now distribute, that's Q2 over Q1 minus Q1 over Q1. Q1 over Q1 is 1, and since delta X is 1, Q2 over Q1 is the base B. And so notice that we've solved this, and we found that R is the base minus 1. So that means the base is R plus 1, or 1 plus R. So we have this basic relationship between R and B. R is our relative rate of growth, our periodic relative rate of growth, or decay, or decrease. So if R is positive, we're increasing. If R is negative, we're decreasing. And it's 1 plus R is the base, or R is the base minus 1. Oftentimes the word relative is omitted, and it's implied by the percentage notation. So if you say it's going up by 5% a year, that is implied that it's a 5% of what it was the previous year, which is actually a relative rate. By the way, you also have to know whether it's increasing or decreasing. If it's increasing, that rate is positive. If it's decreasing, that rate is negative. So if it says, for example, it's depreciating, you have to know that that means it's a negative R. Whereas appreciating would be a positive R. So, if you remember, I told you earlier that there are a lot of important things about linear functions, but if you just had to put one at the top, the most important thing to remember about linear functions is they are exactly the functions with a constant rate of change. Similarly, the single most important thing you should remember about exponential functions is that exponential functions are exactly those functions with a constant relative or percentage change. Another thing that you notice is that the units on the that we have on R, it does have units, and they're always the reciprocal of whatever the x units. So oftentimes x is going to be time. In fact, a lot of times we'll use t for the letter. And if time, for example, is in days, then the R value is a percent per day. Now, you soon get rid of the percentage and make it a decimal. So it's some decimal number per day. So it's really just the reciprocal of the x units. So if R is a monthly percentage rate, then we got to make sure the x value we put in has to be measured in months, not in some other units like years or days. So the following page is going to give a summary of the basic properties of exponential functions that we've studied so far. The graphs that we have there assume that Q0 is positive, but that's not really necessary. The graph looks a little different if it's not. It's flipped upside down over the x-axis. The summary is also going to mention a number e and a number k that we're going to talk about actually in our next video later in these notes here. Okay, but I went ahead and included them here so we'd have a nice one-page summary that would include the e and the k as well. We'll get to that in our next video. So we have seen that exponential functions are those functions that have a constant percentage change or a relative rate of change as, let's say, x is time, as time passes. This means that the amount of increase or decrease in the quantity during one time period is proportional to the amount that you have present. So if there's more there, you get more growth total. Okay, so it's done as a percentage thing, a constant percentage. So here's the question for you. Can you think of some things, some real-world examples that would increase or decrease in this way? Okay, so in other words, another way to say that is, for what types of quantities do the amounts of change depend on the amount present? So actually, just think about that for a minute and try to get some answers and then come back. Press pause now. Okay, we'll come back to the answer to that in just a minute, but let's go ahead and look at this one-page summary. So there are actually two versions of the formula we've looked at so far. Actually, there's another one for a point base formula, but here's a base Y-intercept formula here. And I changed to Q instead of Y and T instead of X, but it's the same thing. But we can also replace base by 1 plus R, and that'll be useful in many applications. We're going to see later on that we can replace the base by e to the k, so we get q sub 0 e to the kt in this type. E is actually an irrational number. It's a number a little bit less than 3, about 2.72, and it's a naturally occurring number that we're going to see actually in these notes, but in the next video a little bit below. Okay, so from a table, if we're given a table of values, okay, where I lost my spot. Here we go. If we're given a table of values, if the first coordinates are evenly spaced, then we're simply multiply the second coordinate by a constant each time to obtain the next second coordinate, or q value. Specifically, if you're going up by 1 each time on t or x, then the y or q is going to be multiplied by the base each time, and we can compute this base from a table as b equals q2 over q1 to the 1 over delta t power. Or if you use the more generic letters, base equals y2 divided by y1 to the 1 over delta x power. If that's the same throughout the table, then it's exponential, and we've got our b, and we just got to maybe plug in a value for t and q here to solve for our q sub 0. So t is time. Doesn't have to be time, but often this is going to be time. Q is the quantity present, q or q of t. Q sub 0 is q of 0, or y sub 0. That's the y-coordinate of the y-intercept. That's the quantity present at time 0. It's our initial amount. B is the base, and it's constant in the table. R is the relative percentage growth or decay rate. And K is what's called the exponential or continuous relative growth or decay rate. So we'll talk more about R and K as we go along. As we look here, here are the basic formulas that relate these. B is Q2 divided by Q1 to the 1 over delta T power. B is 1 plus R. K is the natural log of B. We'll see that a little bit later. And B is e to the K power. And here are your basic graphs. So can you think of some things that will increase or decrease this way? Okay, let's go in and check some of these things. Okay, well, one thing that would be compound interest. Okay, and that's assuming that you're not going to, that the interest rate doesn't change and you're not adding and subtracting money from the account. You just put it in a sum and then let it grow. Okay, we kind of looked at an example of that already. Population growth. If the resources are essentially unlimited, that's often modeled by a constant percentage change. Radioactive substances have a tendency to decay in a constant percentage rate, so that would be radioactive decay. And a good model for depreciation and value of assets would be where they go down by a certain percentage each time, and that would be an exponential decay. So a couple of these are growing, the compound interest and the population, and a couple of these are getting smaller, decreasing, the radioactive decay and depreciation of assets. And there are others, for example, but those might be a couple that are pretty common. So let's go back to our previous exercises 1 and 2 and see if we can figure out the value of R, what its units are, and what it represents. So if you can see if you can do that now. Press pause. Well, if you look back at this, and you may need to look back at your printout here, but in exercise 1, we found the base to be 1.0044600967. So R is just the base minus 1. So take the 1 off, and it's the 0.00446, etc. So that rounds off to about 0.45%, less than half a percent. Now, time is measured in years, so this is an annual growth rate. This is a percent per year. So the population is growing at a relative rate of 0.45% per year. In exercise 2, we found the base to be 1.06, so r is base minus 1, which is 0.06, or 6%. So time is measured again in years, so this is again an annual growth rate. The tuition in that problem was going up at a rate of 6% per year, every year. Alright, let's look at another real-world example where we have some asset depreciation. So in this example, we purchase a new automobile for $15,200. Okay, that's the value when it's driven off the lot, and it depreciates at a value at 17.2% per year. So find a formula for this as a value as a function of time, and time, I guess t would be since we drove it off the lot, and v is the value. Find the value 3 years after it's purchased, and then make a graph of the value of the car. Press pause now. Okay, so we know the percentage rate change is constant from year to year. That makes it 17.2% depreciation every year, so that's what makes it exponential. So I use the formula y equals y sub 0, 1 plus r to the x, but I'm going to change my letters. Change x to t for time, and y to v for value. So then instead of y sub 0, I'll call it v sub 0. That's my initial value, which is my 15,200. Okay? And the rate, remember, it's depreciation. It doesn't say negative, but when it says depreciation, that makes this a negative rate. So that makes the r negative 17.2%, which will change to 0.172 negative. So there's our formula right there. Notice if you do 1 plus a negative 0.172, you get a base of 0.828. Now this ought to make sense to you, because if you're losing 17.2% per year, you're retaining 82.8%, and v is the amount that the actual value, what we've retained, and so each year we're multiplying by 0.828 to get the value of the next year. What's this value 3 years later? That's just v of 3. Plug in 3 in that, use my calculator. In this case, the original data was only about 3 significant digits, so I rounded off to 3 significant digits, approximately $8,630. How about a graph? Takes a little bit of time to experiment with the window, but there's a graph of this. Notice that the amount of increase is dropping rapidly at first. Say from here for a 1-year-old car to a 2-year-old car, it dropped quite a bit here. But say from a 12 to a 13-year-old car, it's a very small amount of drop. And this is more reasonable, say, than a straight line depreciation model for most assets. Most assets drop quicker early on and less later on. And so if you assume that this does by a constant percentage amount, then this would be a good model. In reality, this may be affected by other factors, but this gives you a good basic model to go with. Okay, so let's look at another application, population growth. So the population of a region is increasing at a rate of 0.2% per month. At the beginning of 2000, its population was 12,500. Write an equation giving the population as a function of time. What are the units of R and T? What's the population of the region at the beginning of 2003? And when does the population first reach 20,000? So see if you can work this one out. Press pause now. Okay, now hopefully you worked that on your own, and now we come back to check the solution. Okay, it's increasing, so R is positive, and so R is 0.2% or 0.002 per month. Since that's per month, T must be in months. So R is per month, T is in months. And that'll be the time since the beginning of 2000 in months. So we use the basic formula, y equals y sub 0, 1 plus r to the x power. We're going to change x to t and y to p to be more, indicative of what they stand for, time and population. And our initial y, our initial p, is 12,500. Our rate is 0.002, and so 1 plus 0.002 is 1.002. And we have the formula. Okay? So to find it at the beginning of 2003, Now we have to be careful because t must be in months now. So 2003 is 3 years after 2000, which is 36 months. So t is 36, and we get 13,432, which you can see there. I just did that in a calculator. When does it first reach 20,000? One way we can do that is with the calculator. Graph the original function along with y equals 20,000, find an appropriate window and see where they cross, find that intersection by calc intersect, and we get 235.23 whatever. So that's the 236th month. So it's 236 months after 2000. Well, we might want a year to go with that. If you divide by 12, that's 19.6 repeating. Take away the 19 and then take the 0.6 repeating back times 12, we get 8 months plus 19 years. So it's 19 years and 8 months. So the 8th month is August. So that would be August 2019, or actually about the end of August, or the beginning, well, let's say the end of August. Okay, and we're going to look at compound interest in the next video, so we'll pick up there next time.